Hello, welcome to EPG Pathshala Biophysics, Paper 2, Quantum Biophysics. I am Angshuman Lahiri, Associate Professor, Department of Biophysics, Molecular Biology and Bioinformatics, University of Calcutta. In this paper, today we are going to discuss Module 16, dealing with the outlines of self-consistent field molecular orbital theories. If we consider the theory of Huckel molecular orbital or the extended Huckel theory discussed in the previous modules, we find that we have either neglected the effect of electronic interactions or taken them into account through extremely simple parameterization. However, to correspond to reality, the effect of interaction among electrons should be taken into account as accurately as possible. The self-consistent field molecular orbital SCF MO theory is one way of improving the description by taking into account the effect of electronic interactions. In this module, we shall introduce the basic idea of the SCF MO theory, which has now become a cornerstone of quantum chemistry. The theory will also be discussed in much greater detail in subsequent modules. In this module, our objectives are to introduce the basic idea of the SCF MO method, that is the self-consistent field molecular orbital method, to explain in simple terms the mathematical formalism involved in the method, to describe some of the semi-empirical approximations that make the calculations less demanding, and to describe some of the applications of the quantum calculations in biophysics. So the quantum chemical methods discussed in this module have been developed by many scientists, including physicists and chemists. Some of the main protagonists who have worked on this area include people like Professor Douglas Rayner Hartree, a British physicist and quantum chemist. In 1927, a year after the publication of the Schrödinger equation, Hartree proposed what are now called the Hartree equations for atoms, using the concept of self-consistency. But a significant drawback of his method was that the wave functions he used did not satisfy the antisymmetric condition. It was a Soviet physicist, Vladimir Alexandrovich Fock, who in 1930 noted that the procedure suggested by Hartree did not satisfy the requirement for the antisymmetry of the wave function. A possible solution to that problem was to use a Slater determinant, a determinant of single particle orbitals, for applying the variational principle. After one carries out such calculation, the original Hartree method turns out to be an approximation to this Hartree Fock method, where electron exchange has been neglected. Another noted quantum chemist was Sir John A. Pople, who was a major contributor to the theory of approximate molecular orbital calculations. One of his work was similar to the one developed by Rudolf Pariser and Robert Parr on pi-electron systems, and is now called the Pariser-Parr-Pople method. He also developed the methods of complete neglect of differential overlap, or the CNDO method, and the intermediate neglect of differential overlap, the INDO method, for semi-empirical molecular orbital calculations. In 1998, he shared the Nobel Prize in Chemistry with Sir Walter Korn. For a self-consistent field calculation, we utilize the Born Oppenheimer approximation and disregard the nuclear kinetic energy. So, the molecular Hamiltonian in atomic units can be written as seen in the screen, that is H equals minus half sum over I del I square minus sum over mu sum over I Z mu by R mu I plus sum over I sum over J 1 by R I J, where I and J are the indices for the n electrons and mu is an index for the capital N nuclei. For an SCF calculation, one takes the wave function as one or more antisymmetrized products of one electron spin orbitals. This can be easily obtained through a Slater determinant. One therefore takes a trial wave function psi to be made up of Slater determinants consisting of spin orbitals phi. For molecules, these are molecular spin orbitals. It is observed that the ground state wave functions of many molecules can be represented by a single determinant of molecular orbitals occupied with electrons of paired spins. Such molecules are called closed shell systems. A trial wave function for a 2n electron closed shell system in a shorthand notation for the Slater determinant will look like as shown on the screen. For simplicity, we will consider only closed shell single determinant wave functions like this. In the SCF method, the wave function is usually approximated as a linear combination of atomic orbitals or the LCAO approximation. The exact type and number of these functions depend on the problem. But in general, we can represent the ith molecular orbital phi I in terms of the atomic orbitals phi I equals sum over j Cji chi j. The constants Cji are as yet unknown. As the mathematics of SCF theory is quite involved, we shall state the main results only. For the case of a closed shell single determinant wave function, the variational method yields f phi I equals epsilon I phi I, which are known as the Hartree Fock equations. In this equation, the Fock operator F can be written as F for electron 1 equals minus half del 1 square minus sum over mu Z mu by R mu 1 plus sum over j 2jj minus kj. Here the operator jj corresponds to charge cloud repulsion energy and is therefore called a Coulomb operator. In this equation, we see the form of the operator jj, which is equal to the integral of phi j star 2 1 by r1 to phi j2 integrated over the volume d tau 2. The operator kj is called an exchange operator since it produces exchange integrals. It has to be written with the function on which it is operating, like as in the equation kj phi I1 equals integral of phi j star 2 into 1 by r12 phi I2 integrated over the volume d tau 2 phi j1. An exchange of indices has occurred in the expression for the operator kj. Apparently, the previous equation tells us that the molecular orbitals phi are eigenfunctions of the Fock operator. In that sense, the Fock operator can be thought of as equivalent to the Hamiltonian operator H. However, one should note that the Fock operator is in a way a very strange sort of operator since it depends on its eigenfunctions phi. Since in the expression for the Fock operator the sum over j includes I, we must know the operators ji and ki to be able to construct the Fock operator. But the operators ji and ki involve knowing phi I, which is an eigenfunction of the Fock operator. Therefore, it appears that one needs to know the Fock operator to find the eigenfunctions phi I and also needs phi I to write the Fock operator. One way of resolving this problem is to adopt an iterative approach. One makes an initial guess of the eigenfunctions phi. With this guess, the Fock operator is built, which are used to get the new eigenfunctions phi primes, say. These lead to a new Fock operator, which in turn gives a new set of eigenfunctions phi prime prime. These iterative steps continue until two successive steps do not produce significant changes. When this point is reached, the phi's obtained from the Fock operator will be the same phi's which produce the Coulomb and exchange fields. Since the procedure tries to satisfy self-consistency in this manner, the method is called the self-consistent field or SCF method. If we combine the SCF method of the Hartree Fock theory with the LCAO approximation, one gets the matrix equation sum over j Fij minus epsilon Sij Cji equals 0, and this equation is known as the root-Hahn equation. So let us summarize the procedure that is followed in the SCF-LCAO-MO method. So we first choose the initial coefficients for the molecular orbitals, and next we construct the Fock matrix with these coefficients. We next solve the Hartree Fock root-Hahn equations, and we go on repeating steps 2 and 3 until the input and output coefficients are almost the same. So if we explicitly evaluate all the integrals that will originate in the previously outlined SCF-LCAO-MO method, we get what we call an ab initio method for calculating the electronic properties of a molecule. However, for large molecules, one finds the number of integrals to be prohibitively large for calculations within a reasonable time. Semi-empirical methods were designed to make the calculations faster by replacing the evaluation of some or all of the integrals by parameters or simple formulas obtained from comparisons with experiments. The Huckel molecular orbital method and the extended Huckel theory belong to the class of semi-empirical methods. However, it was evident from the consideration of the theory of Huckel molecular orbital that the method will give a poor description of the excited states or of the geometry of a molecule. Still, there have been attempts in which the pi electron approximation has been retained, but the deficiencies have been addressed. These were made by Pariser and Parr and also by Popel in the 1950s. Both approaches use the basic formalism employed in the Root-Hahn equation and similar integration scheme and have been subsequently combined into what is called the Pariser-Parr-Popel method or the PPP method. The PPP method uses the SCF MO theory for planar molecules considering only the pi electrons. Since compared to the simple Huckel molecular orbital theory, an SCF treatment involves much larger number of integrals, particularly electron repulsion integrals. In the PPP method or the Pariser-Parr-Popel method, some of these integrals are neglected and others parameterized. A key approximation in this method is the zero differential overlap or the ZDO approximation. Let us consider two electron repulsion integrals of the type IJKL, and that is equal to double integral of phi I1 phi J1 into 1 by R12 phi K2 phi L2 d tau 1 d tau 2. In the zero differential overlap approximation or the ZDO approximation, these integrals are neglected unless I equals J and K equals L. In the Pariser-Parr-Popel method, along with the ZDO approximation, the non-vanishing two electron integrals are parameterized in terms of the interatomic distances, the ionization potentials, and the electron affinities. In 1965, Popel and others modified the extended Huckel method in the same way as the Pariser-Parr-Popel method extends the Huckel molecular orbital approach. One of the simplest such extensions is called the complete neglect of differential overlap or the CNDO method, which uses the ZDO but includes all valence electrons in the calculation. The CNDO method utilizing ZDO was considered too drastic for non-planar molecules involving all valence electrons. So, subsequently, an improved method called INDO, that is intermediate neglect of differential overlap, was proposed, which retains integrals of the type IJIJ when I and J belong to the same atom. This method was improved further by Dewar, giving rise to several versions of what we call MINDO, the modified intermediate neglect of differential overlap. Popel also introduced another method called the NDDO, or the neglect of diatomic differential overlap, in which all one center that is monatomic two-electron integrals, were retained. Dewar subsequently developed the MNDO, or the modified neglect of differential overlap method, based on the NDDO approach proposed by Pople. The MNDO method was widely used as a semi-empirical method, but was found to suffer from poor description of hydrogen bond, an interaction important for biological systems. An improved version of MNDO called AM1 or Austin Model 1, proposed by Dewar and co-workers, tried to correct some of these deficiencies involving hydrogen bonding interaction. Other parameterization schemes such as PM3, PM5, PM6 and recently PM7 have been advanced by Stewart and co-workers and have given very accurate results in some cases. The semi-empirical Hamiltonians MNDO, AM1 or PM3 are now available in many quantum chemistry programs. Recent methods such as PM7 are available in a program package called MOPAC, some versions of which are freely available for academic users. The semi-empirical self-consistent field molecular orbital methods have been designed in such a way so that they are computationally efficient, and that means they optimize on their resource usage. Usually, the computational effort required to evaluate the integrals increase as, loosely speaking, as n square for calculations involving n basis functions. For large molecules, the time required for calculations is dominated by the effort required for the solution of the secular equations, which increase as n cube. And to address this, techniques have been developed to avoid complete diagonalizations of the Fock matrix. And what has been done is a pseudo-diagonalization procedure has been adopted that involves transformation of the Fock matrix from the atomic orbital basis to the molecular orbital basis. And with the development of these numerical techniques, it is now possible to carry out the semi-empirical calculations completely in the computer memory with memory requirements that scale as n square. And furthermore, it is now possible to run large-scale semi-empirical self-consistent field molecular orbital calculations in parallel architecture. We can combine many CPUs and run them very fast. In recent years, the availability of graphics processing units, which are popularly known as GPUs, as co-processors in hybrid multi-core CPU-GPU machines has made it possible to accelerate numerically intensive computations substantially. And because of these GPUs, it has become possible to run the most time-consuming parts of semi-empirical SCF MO calculations exceedingly fast. And therefore, it has increased the scope of the calculations by a large amount, making it now possible to treat moderate-sized biological molecules in a quantum chemical manner. Biophysical studies applying quantum chemical methods used to have a number of directions. There are works which focus on the electronic properties of biological substances for an explanation of the experimental data. It is also possible to focus on the correlation between the structure and biological activity. There are other works focusing on understanding biophysical processes occurring at the molecular and submolecular level. The interest in the electronic structure of proteins arose from the measurement of conductance of proteins, peptides and amino acids. It was found that both fibrous and globular proteins had definite conductivities in the dry state. The specific conductance kappa of these substances was found to depend on the temperature, obeying the formula for a semiconductor as kappa equals kappa 0 exponential minus delta E by 2 kT per ohm per centimeter. Cardew and LA in 1959 determined the energy gap for hemoglobin, globin, ferriheme, and a number of amino acids in solid and dry state in vacuo. He found that for hemoglobin, as depicted in the picture, the energy gap is equal to 2.75 electron volt, whereas for ferriheme, the energy gap is only 1.74 electron volt. So in comparison to ferriheme, the conductance of the protein and the amino acids was much lower, and the energy gaps were in the range of 2.7 to 3.2 electron volt. Previously, in 1949, Evans and Gergely considered the possibility of such a band structure in proteins using the LCAO Huckel molecular orbital approximation. The values of the energy gap between the highest occupied molecular orbital or HOMO and the lowest unoccupied molecular orbital or the LUMO were calculated to be between 3.05 electron volt, that is 410 nanometer, and 4.23 electron volt, that is 290 nanometer. These were close to the experimentally observed energy gaps considering the approximations used. On the other hand, the calculations wrongly predicted optical absorption in the region of 290 and 410 nanometer for diglycine, triglycine or polyglycine. To address these and other discrepancies, later calculations turned to SCF calculations with increasingly sophisticated semi-empirical methods. Recently, even ab initio quantum chemistry calculations have become possible, as shown in the publication in the figure, where completely ab initio calculations have been carried out for 55 small proteins. Quantum chemical calculations have been carried out also for nucleic acids, and a major part of these calculations has been devoted to the electronic and optical properties of the components of native nucleic acids. In one of the earlier studies, Pullman in 1958 used conventional Huckel theory to calculate the electronic properties of nucleic acids. Similar calculations were also carried out by Ladik and co-workers. Later, Danilov and co-workers used the self-consistent field Pariser-Parr-Popel method to study the pi electron structure of the Watson-Crick base pair or the tautomerization of bases. And various semi-empirical Hamiltonians, as discussed in this module, are still being used to study low energy conformers of various nucleic acid residues and particularly their modifications. But there is a very important area of biophysics where the application of these quantum chemical methods have assumed a very important role, and this area is modeling of enzyme catalysis. As we all know, enzymes are excellent catalysts. Now, if we want to understand the fundamental processes underlying numerous biochemical processes, we have to understand the mechanisms of enzyme catalyzed reactions. Now, usually enzymes are large and complex biopolymers. Previously, enzymes were thought to be proteins, so enzymatic action was thought to be the property of proteins. But we now know that RNA and even DNA can act as enzymes and catalyze reactions. Since these molecules are so complex, it has proven extremely challenging in many cases to find the mechanisms of their catalyzed reactions and the origin of catalysis from experiments only. On the other hand, such knowledge would provide us with enormous possibilities for developing new medicines or designing new catalysts or enzymes. Molecular modeling involving quantum chemical calculations provide us with a very powerful theoretical tool for understanding enzymatic catalysis, and they are now increasingly complementing experimental studies. Such quantum chemical calculations can easily provide us with information about enzyme catalyzed reactions that are very difficult to obtain from experiments, such as transition state structures and structures of reaction intermediates. For example, these structures help us in the design of new drug candidates. And these drug candidates can, say, inhibit a key enzyme action in a pathogenic organism and thus neutralize it. Also, the quantum chemical calculations can identify important interactions responsible for catalysis. The models can also offer insight into the specificity of these reactions. Now, how to establish the mechanism of a catalytic reaction? This is usually achieved by identifying the groups in the biomolecule involved in the reaction and which functions they carry out. Of most importance is the determination of the structures and interactions of the transition and intermediate states. The difference in the energies between the reactants and the transition state gives us the energy barrier or the activation energy for a particular reaction. And reliable molecular models should be able to predict the barrier height within experimental errors, and if the barrier height calculated for a particular reaction mechanism is significantly higher than what is observed in experiments, then that mechanism is unlikely to be the correct one for that particular case. Quantum chemical methods now provide us with quite accurate calculations for enzyme reactions, which allow us to predict barrier heights within about 1 kilocalorie per mole in favorable cases. One can also calculate the relative rates of reactions for a number of substrates or the consequences of mutating an enzyme at a particular position. Such comparative calculations usually do not require very high degree of accuracy, although they are of utmost practical significance. We can also test hypotheses regarding the involvement of specific groups in stabilization of the transition state in the reaction, which can be very difficult to test experimentally. Moreover, for a proper understanding of the catalytic mechanism, one has to compare the enzyme catalyzed reaction with an equivalent reaction in solution in the absence of the enzyme. Since the description of such enzymatic reactions involve the breaking and making of chemical bonds, quantum chemical calculations are ideally suited to model them. These calculations tell us about the change in the distribution of the electrons and alteration of the geometry of the chemical entities involved in the reaction as the reaction progresses. Since an enzyme is usually a large biomolecule, typically consisting of thousands of atoms, a full quantum calculation involving the entire enzyme is difficult, although not impossible with the availability of modern semi-empirical quantum chemical programs and recent hardware improvement. However, if one needs to use very accurate methods involving electron correlations, then calculations have to be restricted to smaller sizes. A very useful approach in this regard is the development of what are called the quantum mechanics, molecular mechanics, or QMMM methods. In QMMM approach, a small cluster of atoms involving the functional groups that take part in the reaction is selected and treated with high-level quantum chemical methods. The rest of the enzyme and the solvent molecules are treated in a classical manner with an empirical force field approximating the Born Oppenheimer potential energy surface. In many treatments, the two regions interact with each other, and since this again involves approximations, there are a number of ways the energy of the system can be evaluated. Once the effect of the environment has been taken into account, a reaction path is followed within the QM region in small steps, and the minimum energy structures are obtained for the selected reaction coordinate. And lastly, the complete energy profile over the entire reaction path gives the transition state structures and barrier heights. Let us summarize the main points of this module. We have learned how to construct the Hartree Fock equation for a molecular Hamiltonian under reasonable approximations, and also learnt about the mathematical formalism to solve it using the SCF-LCAO-MO procedure. We discussed how to construct the associated root-Hahn equation and its utility. We examined also the SCF extension to the Huckel molecular orbital theory and the extended Huckel theory in the form of the Pariser-Parr-Popoul and complete neglect of differential overlap methods. We also briefly discussed some of the improvements that have been proposed over the years for these semi-empirical SCF methods. And lastly, we discussed a few applications of these methods in molecular biophysics.